right, so I wanted to give you a little view of what it would be like to use the position and velocity update equations in running some code. Remember that in the last video I created, I showed you an analytical example, taking derivatives of position and velocity in order to get other things. And that's a pretty typical physics class type thing to do. But in this one, I would like to take you through a little coding problem. Now, this is something that I'm sharing with you so you can look at my code. So here's the link to my code. I've made it public and you can access it through this link. Just copy and paste if you'd like. It's just a simple example of a sphere moving through space. So it's not the same as matter and interactions problem number 78, but I did start with their code to get going, and so I'm going to go ahead and credit them here with the beginning at least. Okay, so this is matter and interactions, probably 778 in chapter 1 with modifications. All right, so let's take a look at this code. All right, so let's say that I started off with this code. Okay, it always starts off with this from visual import star thing, and that's the first line that draws in the libraries that you'll need to run visual Python, VPython. But then we go through and I wanted to identify certain things in the code that are the physics, the core physics of it. Okay, so I'm going to define a particle and it's going to be a sphere, and I'm going to place it in space and give it a size and a color. Okay, so that's what this whole bit does. Particle equals sphere. The position is the initial position vector for my sphere. Now, this is a 3D problem. So here I say pos, that's position, equals vector, minus 5, 0, 0. So let's imagine it could be, I could change the dimensions here in my head, but I'm going to go with standard dimensions. And so this means that the position of my sphere is at minus 5 meters in x and 0, 0 in the y. Okay? The radius is 0.3 meters. The color is cyan, and then this statement right here, make trail equals true, that just means that when I run the code, I'll be able to see the path of the particle that it traces through space. Okay? It'll leave a little trail behind, like signs, okay, or a tracker. Okay. So the next bit, I'm going to define another variable. I'm calling it v. This is my velocity vector. Okay, so v equals a vector. Okay, so it's a vector and it has x, y, and z dimensions of 0.5, 0, and 0. So this means that my initial velocity, here's v initial, my initial velocity of this sphere is 0.5 meters per second in the x and nothing in the y or z. So it's traveling at x. Okay, I define a delta t. Okay, so this is the interval that I'm going to take in between time steps. So how computer programs work is it goes through little intervals in time. Here we define our delta t as 0.05. Using SI units, I choose to interpret this as 0.05 seconds. Okay, so it's going to figure out what happens at x equal to, or t is equal to 0. Then it's going to figure out the position and the velocity vector at t is equal to 0.05 seconds. Then at t is equal to 0.1 seconds. Then at t is equal to 0.15 seconds, and so on. The time steps, in other words, are 0.05 seconds. I initially define my time. Okay, so this is my initial time. T is equal to 0. So I'm going to start my clock at t is equal to 0. Now here I have this while loop. While t is less than 30. That means as long as my time is less than 30 seconds, I'm going to do these things. Okay, so while t is less than 30, I'm going to run these steps. This is a rate step. They'll talk about that more in your VPython. Don't worry about that too much right now. Okay, next, my next important physics thing is this. Particle pos, my particle position is equal to my particle position plus v times delta t. Now this is my position update equation that we covered in the last lecture. Basically, this is saying our final is equal to our initial plus v average times delta t. All right, that's what it is. Now you might go, wait, it says particle pos is equal to particle pos. Mathematically, that doesn't work out. This is where computer science and physics and math differ. What you can do is it would be annoying, for example, to constantly have to go in and add a new variable name every single time you updated your time and position in a program, right? You'd start off and you'd have R initial, and then you'd have R1, R2, R3, R4, R5. Then you'd have so many variables that it's just a hot mess. So computer science says, okay, let's not do that. I don't want to do a new variable each time. I'm going to allow a redefining of what my position is. So I'm going to take my time, I'm going to take it at my time t0, for example, and I'm just going to update that, and I'm going to put that back in the same memory bank in my computer. So this is where math and science and computer science differ a little bit. That would really be a faux pas in math and science, but it's fine in computers, okay? So you can think of the particle pause on the left-hand side as being your R final, and the one here on the right-hand side as being your R initial. But please don't do that on your analytical homework. I will rip you a new one, okay? All right, then after that, I'm going to update my time variable, right? So this is now T final here on the left-hand side, and then that's equal to T initial plus delta T, okay? So I'm updating my time variable. So it might start off here on the right-hand side at 0, and then after it performs the operation, it's 0.05 seconds because I've added 0.05 seconds to it. Okay, so that's what the code does. That is the physics behind the code. Now, I want you to look at this and think about what's going to happen to this particle, okay? So it's got an initial x position, the initial y and z position are 0, so it's got an initial position of -5 in the x. I've given it a velocity of 0.5 meters per second in the x direction. What do you think is going to happen? Okay, so what's that going to be? So now that's the code. Now let's run it and see what actually happens. Okay, was it what you thought was going to happen? It was what I thought was going to happen. This left-right is my x direction. See the make trail? It shows you a little line where the particle was, and your particle is this cyan sphere. It started off here at t is equal to 0, and it traveled at a constant rate to the right, okay? All right, so that's what I thought was going to happen. Good. Straight line motion. So cool. Not super interesting, but I was able to model it, and I was able to show what happened, okay? So that's what the code did. But like I said, it's not super interesting, okay? That's really boring. So let's see if we can make something else happen here. So what I'm going to do is I'm going to add in an acceleration, okay? This will change my velocity. Look here, here's my acceleration vector. A is equal to a vector 0, 0.050. So this means that it's got an acceleration of 0 in the x direction, 0 in the z direction, but then an acceleration of 0.05 meters per second squared in the y. Then what I do here is the only other line I added to the code is this. After I update my position, I also update my velocity. V is equal to V plus A times delta T. Well, that's my velocity update equation, right? V final is equal to V initial plus A times T final minus T initial. So that's it. That's it. So I've added an acceleration. I go through, I start my clock at t is equal to 0. I define my delta t as 0.05 seconds. I give it an initial velocity, an initial position, and an acceleration. Then I say, okay, I'm going to update my position, and then I'm going to update my velocity, and then I'm going to update my time, and I'm going to do that all while t is less than 30 seconds. So what do you think is going to happen since my initial velocity is in the x direction and I added an acceleration in the y? What do you think is going to happen? Well, to me that sounds like a turn, okay? So let's go back to the code, okay? Now to save time, I commented some stuff out. I'm not going to talk too much about that. Just understand that I did it. Okay, so now it's active in the code, okay? And I'm going to run it, and let's see what happens. Look, it's turning. Okay? Okay, that's it. So it starts off with a velocity in the x direction. It keeps that velocity. It keeps walking to the right, right? But then I also applied an acceleration in the y, which made it turn upward here, okay? And it changed my path. And that's exactly what happened. Okay, great. So I'm able to model some physics there. So that's real physics. Okay, so the question comes then, How good is that prediction? Like, I modeled it, okay? Does that mean it's right though? Does that mean that it checks with what does that mean that my analytical solution would be the same as what my code predicts? How good is my prediction? Can we check it? And what would happen? See, I talked in an earlier lecture about the importance of what your time interval was here. What would happen to my code if I changed this time interval to something, say, longer, right? Like, let's say I wanted my code to run faster, okay? How could I check it? Okay, so what I've done here is to check my code against the analytical solution. I want to know what the real value is. Now, this is a little bit more advanced, but here I go. I just added in a print statement. Okay, so I added in print. So actually, I'm sorry, here, let's go here. I really added in a print of all the things. So I'll fix that. See here. Okay, I added in a print of all the variables, okay? So I just wanted to know what the time, the position, and the velocity vectors were. So here's my print. It gives you the list, time, position, velocity equals, so it's going to print that out so that you know what order things come in. And then it's actually going to print the values of my variables, t, particle dot pos, and v. Okay, so it's going to print those values for me. And I'm going to run my code. Okay, so I'm going to see what it thinks those values actually are. So let's run it. Okay, so the code isn't going to change in the path. The path that it traces out is going to be the same path that it traced out before. But now, every step along the way, it's telling me exactly what those values are, okay? And it's going to run this code for me. It just takes a few seconds. And then what I can do is I can look at the very last value reported and check it against my analytical solution and see if it's right. Almost done now. 27 seconds, 28, 29.95. Okay, now remember the loop said while t is less than 30. So on the next step, it would have been 30, so it cut itself off. So the last time that it reports is 29.95 seconds, and then here's my position vector. My position vector is 10 meters, 22.4625 meters in the y, and then 0 in the z. And then my velocity vector here is reported as 0.5 meters per second in the x, 1.5 meters per second in the y, and 0 in the z. Okay, so that's my values, see? It shows me the vectors in these little arrows, okay, within these little, I guess, triangular brackets, okay? So going back to my PowerPoint now, how good was that prediction? Okay, so what I can do is I can check it against my theoretical values. Now in chapter 2, we're going to get to a review of our kinematics equations, right? But for now, I want you to remember your 1000 level physics class and remember that this was for a constant acceleration what your equation was. So your final position, R final, is equal to R initial plus V initial times T plus 1/2 times your acceleration times your time squared. That should look super familiar from 1000 level physics. If it's not, pause the video, go back, look it up, refresh your memory, but don't worry too much about it because we are going to cover it in a later lecture in chapter 2. For now, you can trust me, okay? Now, I'm going to check the accuracy of my prediction. So we defined in our code what the initial position, the initial velocity, and the acceleration vectors were. My initial position was minus 5 meters, 0, 0 in the y and the z, minus 5 meters in the x, in other words. My initial velocity was 0.5 meters per second in the x, and 0 in the y and z. And my acceleration vector was 0 in the x and the z, and 0.05 meters per second squared in the y. Okay, so that was my initial definitions there. Okay, so I can plug those things into this equation and use the t final that got reported at the end there, which was 29.95 seconds. Okay, so I can use my 29.95 seconds and these things to figure out what my final position was. And I can also use the velocity update equation, that v final is equal to v initial plus acceleration times time, and the 29.95 seconds at the very end, and see how those values check out. So I can check the accuracy of my code against theoretical predictions. So when I do that, right, the theory says that my final position should be 9.975 meters in x, 22.425 meters in y and 0 in z, and that my final velocity should be 0.5 meters per second in x, 1.475 meters per second in y, and 0 in z. Now, our code printed out what our final values were with that t is equal to 0.05 second interval, and you can see that they don't quite match the theoretical prediction. Look here. I got 10, 22.4625, and 0 from my position. So I'm off by about 4 centimeters, right, in my y. I'm off by about 4 centimeters. Okay, and in my final velocity, I'm off just a little bit in my y velocity. So I had 1.475 was my theory and 1.5 as what the code predicted. Okay, so I was off a little bit there. Okay, so you might say to yourself, well, what would happen? That's not a bad prediction. I mean, being off by 4 centimeters was pretty good, right? So maybe we could increase our time interval and it wouldn't matter too much. And that would make our code run faster, which would be nice, right? So let's do that and let's see what happens. So if I go back and I edit the program and I change my delta t to something like 0.2 seconds, right? That doesn't seem like it should be such a big deal, right? Now I have a 0.2 second time interval, and I'm going to run the program. And let's see what happens now. Okay, well, first of all, look how much faster my code runs. Oh my gosh, that's so nice. Wow, so much faster. My final value here is 30, right? So that's my 30 seconds. It actually made it to 30. And then I have my position and my velocity vectors defined here. Now I'm going to copy those over from here and put them on my slide, okay? So let's see. How did it do? How did it shake down against the theory? So the theory, if I plug in 30 seconds for my final time, the theory says that my value should be 10 meters, 22.5 meters in the y, and 0 in the z, right? So 10 in the x, 22.5 in the y. And then my final velocity is 0.5 meters per second in the x and 1.5 meters per second in the y. Okay, so let's compare that against the what the code gave. So copying and pasting from the code, you can see here, I got 10.1 in the x, 22.65 in the y for my position, right? And then for my final velocity, 0.5 and 1.51. So I'm still pretty good on my velocity. That's still pretty decent prediction. But let's look at my y position now, right? It's worse. My prediction is worse. Now I'm off by about 15 centimeters in my y position. Remember, I was just off by 4 before. But my code ran a lot faster. So you just have to ask yourself when you're coding, how accurate do I want to be, right? How accurate do I want to be, and how long do I want my code to take to run? So you might think to yourself, well, gee whiz, I want more accurate than that. That stinks, okay? All right, no problem. We can go back. Hey, let's do even better. Let's not run it at 0.05 seconds. Let's run it at 0.005 seconds, okay? Let's try that. I mean, heck, we could get really accurate then. All right, here we go. Oh my God, this is so slow. It is so incredibly painful, okay? I don't even know if I can make it in this video with this running all the way through to the end, okay? It's just too slow. Now, of course, I could speed it up if I were on a different computer or maybe if I weren't on a web-based browser, and it might be worth it to you, okay? It might be worth it to you to get a super accurate prediction if that's what you want. But for now, I'm not even going to wait till the end of this video. I'm just going to stop it right here and say that you see the balance in coding. Sure, I might get more accurate, but boy, does it take longer to run. Okay, well, I hope you enjoyed that and understood everything. And I will see you next time, okay?